up, guys? Welcome back. Hope you had an excellent weekend. I did myself. I spent a lot of time hanging outside with the family. I also refurbished an old school welder, and I got it working again and started melting metals. It was fun. Melting metals with electricity. It's kind of one of those weird things you think about, like directing electric flow in such a way that it melts metals together. Seems really dangerous, right? Anyway, I had a nice time. I hope you like my new intro. The new intro for our course. I'm just having a little fun. Trying to figure out some editing software. And for the past couple of weeks, I've been like here and there dabbling with it to see what I can do. And then this morning I decided, you know what? I'll go ahead and knock together an intro for the courses. So hope it wasn't too startling for you, and I hope you enjoy it. Okay, so moving forward, we want to continue through our chapter discussing single component equilibria. Okay, we have come to a juncture where we've discussed, or we have written out the Clausius-Clapeyron equation. Right, and we've also written out the, let's see if we can find it up here. We're getting close. Clapeyron equation. Okay, so we have the Clapeyron equation and the Clausius-Clapeyron equation, which both relate the change in pressure versus the change in temperature. So I'm going to flip back to this. The change in pressure with respect to the change in temperature. Okay. So remember that. We're going to come back to that in a second. Now, most of you have seen something called a phase diagram before. Whether it was in Gen Chem or in A Chem, somewhere in your chemistry life, you have seen a phase diagram. A phase diagram is essentially a graph. A graph that represents the phases that are stable with respect to pressure, temperature, and volume. Okay, so it represents the stable phases that are present with respect to temperature, pressure, and volume. Typically, these are two-dimensional, and they usually are in terms of pressure and temperature. So you usually have a pressure-temperature phase diagram. Sometimes you can have a three-dimensional phase diagram as well that includes the volume component, but that is not as typical as the pressure-temperature. Now, a typical phase diagram, see if I can draw straight lines today. Okay, we have pressure on the y-axis and temperature on the x-axis. And let's not make it so certain. Gosh, I can't think of the word. Let's not make it in degree C just yet. I want to come back and make it more specific later on. Right now, let's just keep it general. Okay, so we have temperature and pressure. And typically on these phase diagrams, you'll have lines like this. And maybe something like that. And you'll have a couple of different points. Okay, this is what a very common typical phase diagram would look like. So you have the region over all the way to the left is the solid phase. So the solid phase is stable there. In the middle upper portion, the liquid phase is stable. And in the bottom portion, the gas phase is stable. Okay. Now, there are some lines here. Okay, so I'm going to draw some points. I have point A. Let's draw point B over here. And then let's draw point C down here. And then maybe let's just throw in point D right there in the middle. Okay, point A is directly on what's called the fusion or melting line. This is the line at which the pressure and the temperature are such that this system is melting or in the state of fusion, okay? And this line here is the vaporization line. And this line down here is the sublimation line. Okay? So the lines, they represent the conditions where a phase equilibrium occurs. Okay, so they represent the point at which a phase equilibrium occurs. And what does it mean to have a phase equilibrium? What does it mean? Let's look at an example. Okay, so point A, let's look at point A. Point A is directly on the fusion melting line. Okay, so if P is equal to PA and T is equal to TA, where we have PA is just this point here and TA is this point here. Okay, if we have a pressure equal to PA and a temperature equal to TA for this substance would be melting. i.e., the solid and liquid phases are at equilibrium. Okay, so that's what it means to be directly on top of the line. You have these two phases that are in equilibrium with each other. Okay, now likewise at point B, let's see, B, we have pressure is equal to PB, temperature is equal to TB. Okay, up here at point B. Point B is on the vaporization line. So the substance is vaporizing. In this case, the liquid and the gas are at equilibrium. Okay? And then finally at point C, on the sublimation line, when we have P equal to PC and T equal to TC, the substance is subliming. For example, or i.e., the solid and gas phases are at equilibrium. Okay, so we have the melting fusion line. What else do we have up here? Melting fusion line, we have the sublimation line, we have the vaporization line. We also have this point here called, not TC, TP, which is something you guys might not have very much of. He's got jokes. TP, this is called the triple point, not the toilet paper, the triple point. The triple point means that all three phases of this substance are at equilibrium, okay? So we have, well, let's write them all out, okay? We have the melting fusion line. This is a solid and a liquid at equilibrium. We have the vaporization line. This is where a liquid and a gas are at equilibrium. And we have the sublimation line, where a solid and a gas are at equilibrium. Next, we have the triple point. Okay, this is where solid, liquid, and gas are at equilibrium. Okay, we have one more point on this graph, and it is called the critical point. And it's up here at the very top of the vaporization line. Well, maybe I should write this. Anything above this critical point is said to be a supercritical fluid. Okay, when you have a supercritical fluid, it is a critical point. When you have a supercritical fluid, it is basically a fusion of the liquid and the gas phases. Okay, so it's a fusion of liquid and gas phases into one indistinguishable phase called a supercritical fluid. Okay, those are the points that are of interest within a typical phase diagram. Okay, and then finally we have point D up here, right? I drew a point D right in the middle. So if we have a pressure of PD and a temperature of TD, we only have one stable phase. This is right in the middle of the liquid, so we know that the stable phase there at point D is a liquid. Okay, so if we have pressure of D and temperature of D, that is a stable liquid phase. But what do the lines actually mean? What does it all mean? That was a really bad mean. Okay, what do the lines actually mean? Well, if we think about it, they are the change in pressure with respect to the change in temperature. Dun dun dun. And as I just mentioned at the very beginning, this is important, right? Because we can write this as dP over dt, and let's just start ringing some bells here. So the change in pressure over the change in temperature is simply the line. And we can calculate this with what? Raise your hand. Anybody got any ideas? No, nobody's raising their hand. Oh yes, you in the front, Mr. Mixed Student Face. Student Mixed Student Face. What is the correct answer here? Well, you can calculate these with the Clapeyron or with the Clausius-Clapeyron equations. You are absolutely correct. You can calculate these with the Clapeyron. I'm just going to call that the clap. We can calculate that with the Clapeyron equation or with the Clausius-Clapeyron. Or as I like to call it, the Clausius clap, or the Claus clap. Okay, remember the change in pressure with respect to the change in temperature is equal to the change in the molar entropy over the change in the molar volume. This is the Clapeyron equation, right? And, or at least a form of it. And also, with the Clausius-Clapeyron, we define dP dt as being equal to the change in the molar enthalpy over temperature times the molar volume of the gas. Okay, this is one form of the Clausius-Clapeyron equation. So phase diagrams, it turns out, they are simply plots of the clap. Okay, they're simply plots of the Clausius-Clapeyron or the Clapeyron equation for a particular given substance. Now think about that. You have been seeing phase diagrams since your beginning days in chemistry, and just now, you've been given the truth of what they actually come from. The Clausius-Clapeyron equation. Are you blown away? You should be. Now let's look at some phase diagrams for a couple of different substances, because it turns out that they don't, not all phase diagrams are created equal. right? They're going to be different depending on the substance that you're looking at. So let's look at pressure in ATM versus temperature in degrees C. And let's look at first the CO2, or the phase diagram for CO2. Okay, so in CO2, it kind of starts down here, and then it swoops up, and then we have this triple point here, and then the melting fusion line goes up, and then the vaporization line goes out, and then we have the critical point there, something like that. Okay, so we have solid here, we have a liquid here, and we have a gas here. Now, at 1 atm, right, that's atmospheric pressure, and negative 73.4 degrees C, oops, negative 78.5. Can't get that wrong. Negative 78.5 temperature. We have basically an equilibrium that exists between the solid and the gas. This is why at atmospheric pressures, when you have solid CO2 or dry ice, it doesn't go into the liquid phase before it turns into a gas. It goes directly from a solid to a gas. It has everything to do with the solutions to the Clausius-Clapeyron equation, which define this phase diagram. The triple point exists at 5.11 atmospheres and a temperature of negative 56.4 degrees Celsius. Okay, and then if you go above that temperature and above that pressure, you get to the critical point up here, which is at 73 atmospheres, so extremely high pressure, and temperatures of around 31.1. So a balmy day, essentially, but crushing pressure. That's when you can become a supercritical fluid of CO2. Okay. Now let's compare that to the phase diagram for water. Water is everybody's favorite molecule. It's just such a neat little molecule. And it's such a neat little molecule because it has a bunch of weird things that are true about it. Which the phase diagram points out one of these weird things. Okay, so let's start out with water. It does something like that. Up to the triple point. Holy moly, that's loud. Sorry. Now the entire world knows that I just got an email. Okay, so I have the sublimation line there up to the triple point. And then with water, it kind of goes like this and up. And then it goes over like this to the critical point. Okay. This triple point exists at a pressure of 0.00611 and a temperature of, 0.01 degrees C. Okay, that's the triple point. So super low pressure and about freezing temperature is the triple point. The supercritical point, however, is even more crushing pressures than CO2 and temperatures that are pretty high. Okay, 374 degrees Celsius and 215 atmospheres of pressure is the the critical point at which water becomes a supercritical fluid. And of course we have the solid phase and the liquid phase and the gaseous phase here. Now, there is something weird about water's phase diagram that's different from water, and it's only true for a few substances. And that is the fact that the melting point, or the melting line, fusion line, the fusion line has a negative slope. If you look over here, the fusion line for CO2 has a positive slope. Okay, most substances have a positive slope in the fusion line, and if you let's think about what this means. What it's saying is, as we increase the pressure, as we're going up on the pressure scale, most substances tend to form more and more solid phase. So the solid phase becomes more and more stable as the pressure increases. And this has to do with the fact that the solid phase is generally less dense than the liquid phase. Or, excuse me, more dense. The solid phase is usually more dense than the liquid phase in most substances. But in water, and a few other things, for example, bismuth, in water, the liquid phase is more dense than solid. Okay, the liquid is more dense than the solid. This is not true for most things. Usually, the liquid is less dense than the solid. But in the case of water and bismuth, the liquid is more dense than the solid. And so as the pressure increases, liquid becomes more and more favored for these high pressures. Okay, so that's kind of a weird thing about water. And it's actually kind of useful that water acts this way, because if it didn't, then lakes would freeze from the bottom up rather than the top down, right? And essentially all of the life that existed on the bottom of the lake would freeze. Yes, that would completely disrupt life on Earth and probably would have resulted in a completely different evolutionary timeline. So, thank you, water, for being different and having a negative slope. Okay, so we've talked about natural variables. We've talked about the 4 equations of energy in terms of their natural variables. But what I want to introduce now is this idea of actually talking or describing the chemical potential, mu, in terms of the natural variables. Kind of sounds like a kid's book title. Mu and the natural variables. Right? It's like the adventures of Mew and the natural variables. Oh, it's Monday, right? Kind of feels like a Friday evening for some reason. Can we define mu in terms of some natural variables? Essentially, what we want to know is how the chemical potential changes with respect to pressure and temperature. If we have all of these plots that show the phases of pressure as with respect to pressure and temperature, what we want to know is the chemical potential and how does that change with pressure and temperature, because we want to be able to see if something is a spontaneous process or not. Okay, so essentially what we want to know is we want to know how mu changes with respect to pressure, and we want to know how mu changes with respect to temperature. Now recall that the Gibbs energy is equal to mu times n, okay, essentially. If we do a bunch of math from basically recalling a bunch of things from chapter 4, when we went through this in more detail, we can essentially write the change in chemical potential with respect to the change in temperature with pressure and number of molecules constant equal to negative S hat, or the molar entropy of the system. And we can express the change in chemical potential with respect to pressure with temperature constant and N constant as equal to the molar volume. Now, knowing these two partials, we can combine this into a natural variable equation that looks something like this. d mu is equal to negative S dt, or S hat dt, plus V hat dp. And this should look very similar to you. This looks a lot like the natural variable equation for G. Okay. And we can rewrite this we can rewrite it as the change in delta mu. So how delta mu changes with respect to the change in the temperature at constant P is equal to negative delta S. And we can also write the change in mu, or how delta mu changes with respect to pressure at constant temperature, is equal to delta V. And both of those are molar quantities. Okay, what does this actually help us with? Amazingly enough, this guy here, well, let's make this red. Okay. This guy here has to do with entropy, and entropy is all about spontaneity, correct? Actually, it was our first definition for spontaneity within a chemical process. So you can see that as the change in temperature decreases, or how about when the delta T increases, right? So as temperature is increasing, this dt function goes up, and we see that we have a corresponding negative change in entropy. A negative change in entropy that's happening here. And actually, this ends up explaining why a substance melts or vaporizes at elevated temperatures. Okay? It's all a function of entropy. If you increase the temperature, you must therefore melt or vaporize. Okay? And the second one here, this one explains why substances usually freeze at high pressures. Of course, this does not include water. Okay, so at high pressures, the volume is condensed enough that it shows how the density of that solid must increase, right, with the change in pressure. So it explains why it should freeze at high pressures. There is a huge explanation and discussion of these last two little blurbs that I've given summaries for. I think it would be very helpful for you to go through and essentially read through those and learn those reasons and learn the practical understanding of these two equations here. This is a really useful thing to understand about phase diagrams in particular, is how these two equations relate back and can tell us about what's happening with the various phases within a substance phase diagram. Okay, that's actually it for chapter 6. So we're done with chapter 6. We are going to move into chapter 7 on Wednesday. Yeah, I hope you guys have an excellent day, and I will see you next time.